Okay, so here we are on our last reading of the semester, event-related potentials. The quantity of slides in this are not super high, so much as it's going to take a second to talk through some of the diagrams. So, event-related potentials, or ERPs. Event-related potentials, I will call them ERPs from here on out because that's what people do, are part of the subfield called neurolinguistics. Neurolinguistics, like psycholinguistics, is interested in real-time language. Well, here I see use, but use in like the sense of processing. It's kind of hard to do it with production, but that's a question for a whole nother day. Neurolinguistics differs from psycholinguistics in that its models are focused on the brain structure and the relationship with that structure and language. Therefore, the accompanying methodology has to be distinct. You know, reading times can relate to some degree, but they are too lengthy in some sense to be useful in this context. And we'll see other ones and you can kind of compare as we get there. Now the brain, language and brain. What's the brain got to do with it? Whether we're aware of it or not, much of linguistics is a study of the faculty of the mind. That is to say, what we think, how we plan, those are functions of the mind. And the mind-brain connection is less well understood than we may think. You know, neurolinguistics is very popular because there's this feeling that we're going to crack the code of how the physicality of the brain is going to translate into language. And I'm here to tell you that's overselling it to some degree, right? And you'll see what our methodology is, and then maybe you'll get it. When we say something, for example, I'm talking about the brain-mind connection. Let's think about intelligence. And here I'm going to use the word in quotations because it's so many definitions. But if we want to say someone's intelligent, whatever that means, or even intelligent in a specific way, like musically intelligent or language intelligent or interpersonal or mathematical or whatever it is, it's unclear what that means in terms of brain function or structure, right? Is their brain better? Is it more efficient? What does that mean, right? I mean, there are some unconfirmed hypotheses that people have played with, things about general intelligence, which is called G for short. G stands for general, but G, or general intelligence. So people have proposed maybe the neural connections are either more efficient or more plentiful, right? The brain works in some better way. Completely unconfirmed, though. Completely, right? Because testing it is incredibly difficult. So language in the brain, are we stuck? Are we without any tools whatsoever, I would say? I mean, the question is this, if we don't know how intelligence in the brain works, and everybody has an opinion about intelligence, right? You could give them math problems and try to scan their brain. If we don't know how that really works convincingly, it's kind of a stretch to say we know how language in the brain works. And this is not to say, again, it's not that there's no research on this, but it's a stretch, right? But we do know there's a relationship between the structures of the brain and how the mind works or how language works because of aphasias, right? It's very clear there is a relationship. But, how is that information stored? How is that information accessed? Is the rest of the brain involved? It's really not transparent. Not really, especially given the tools that we have at our disposal. Our two major tools that we would use in neurolinguistics. You're seeing images here on the right, okay? And I'll talk about them individually in a second. The first one is fMRI, or functional magnetic resonance imaging. It's sort of the same thing they do for medical purposes. And the one on the bottom, oh, and fMRI is neuroimaging, or pictures of the blood or oxygen flow in the brain. So what we're seeing there is probably deltas in the oxygen flow. And the second picture is a mapping of ERPs. ERP, what it's doing is doing voltage mapping to the scalp, and the voltage is resulting from neurons firing. And we're going to see more about that in just a second. But ERPs and fMRIs have different strengths and weaknesses, right? fMRIs, one of their strengths is that their picture is more comprehensive. You know, if you look at the Wikipedia article on neurolinguistics and you look at the fMRI section, what they'll tell you is that the location specificity is great for fMRIs, but as a weakness, not only they're extremely expensive, and they are, researchers just don't get a hold of this unless they're affiliated with a hospital, but they're harder to time sync to stimuli, in the sense that it's hard to know what's the relationship between a change and the onset of a stimulus, right? It's slow because blood flow is comparatively slow. ERPs, for their part, are dynamic and they're quick In fact, the time windows for ERPs are less than a second usually. They are affordable in comparison, right? You need kind of a voltage cap and electrodes to touch your scalp. You got to get gel to stick them on there, something to clean people's hair with afterwards. Usually you need a soundproof booth, you need a screen. You know, it's comparatively more affordable. Like linguistics labs might have their own without having a hospital involved. Weaknesses, however, is we have to infer what's happening based on voltage on the scalp. That's kind of removed, right? So at least in fMRI, we are literally looking at brain structures. And ERPs, which are the tool that we most readily have at our fingertips, we're doing voltage, you know, and we have to, you know, interpret a lot of what we're looking at. Okay. And of course, the effects that we can look at are very short term. And when I say short term, like I said, a second or less. Compared to an fMRI where you have no time sink, really, that's great. But compared to, let's say, reading times or eye tracking, you've lost a lot of things, right? Because you can do self-paced reading across an entire sentence. You can do eye tracking across maybe a paragraph if you're lucky. But ERPs, you get that split second after the onset of a stimulus, and after that you don't know what you're looking at. So it's really short term compared to particular stimulus. So there's pluses and there's minuses. Now when I say voltage on the scalp, here's what we saw before, and let me talk you through this graph so that when we look at pictures of hypothetical scalps in a second, you'll be able to kind of go back to what we're looking at here. You see your x-axis is labeled time after stimulus and milliseconds. And you'll notice that voltage on the y-axis is called potential because they're event-related potentials. The stimulus onset is what you're seeing at 0 on the x-axis, and no voltage would be 0 on the y-axis. And that lovely line up here, that's our 0 on the y-axis. Notice how far up it is. Positive voltage, for no particular reason that I'm aware of, and I've had other neurolinguists tell me this, is mapped down. Notice that +3 is below 0 in this map, this in this chart. And negative is above 0. Why do they do this? No one knows. But well, no one anymore really knows. Maybe you would go, if you really, really, really look, you'd figure it out. But it's just a convention at this point. Okay? So here, what we're looking at is changes in voltage, right? We're seeing bumps down, bumps up, bump down again, and then a big bump down, right? And if I were a researcher, I would say, well, I'm seeing a negativity around 120 milliseconds, and the biggest positivity I'm seeing at 400 milliseconds, okay? And so they get called things like N400, for example, is a very common, they call component, right? An observed reaction they call components, right? Electrophysical components. And so an N400 would be a negativity at 400 milliseconds, and a P600, which we'll see again in a second, is a positivity at 600, which is down, of course, okay? Now when I say voltage, it's kind of like this, okay? Usually if they're going to represent voltage on a scalp, it's done like this. So you see 3 tops of heads. You see the electrodes the way that they're usually laid out. The nose is always up. The ears are left and right. And so the idea is you're looking at the person from above, like you were a bird observing them, and hopefully not going to mess up their hair. Then we see the colors, which is positivity and negativity. Positivity is typically red, negativity is typically blue. You can also see that on the left side, like a weather map. And the middle one, N400, comes up in our reading. It's a negativity 400 milliseconds. Notice how an N400 is kind of spread all over the scalp. It's pretty much everywhere. Whereas a P600, which is positivity at 600 milliseconds, and you'll notice below there's actually ranges, but that's what it gets called as a P600, is pretty far in the back, actually. So there's some discussion to be had about the relationship between the structures of the brain, but this is only voltage on the surface. We don't really know what it is underneath. Okay, people have opinions, but it's not clear. Now, some claims made about these specific, and we're going to zoom in on N400s and P600s because they were in the reading and they are the most common things you're going to see in the literature. When they receive attention in neurolinguistics because they have claims made about what they mean or what they correlate with. I'm saying correlate because there is not causality here. We don't know what's causing it. So you must talk in terms of correlation with neurolinguistics because this is where we are right now. I'm not saying it's not going to evolve in about another 30 years and suddenly we can have a discussion about causality. But correlations, definitely. So an N400 is claimed to be visible or to correlate with semantic violations. And the original author is here on the right, and this is also in the paper if you want what the article's called. And it'd be something like, he spread the warm bread with butter is like the normal sentence. So normal's blue. And then the violation is red. He spread the warm bread with socks. Yuck. Okay. So this, in theory, when you hear socks, should elicit an N400, a negativity 400 milliseconds. A P600 is claimed to be visible for syntactic violations. And as someone who has an opinion about syntax, I find this one odd. Usually what they mean by syntactic violations isn't morphology or something like that. It's word order. So funky word orders. So that being, and again, here's the citation for the initial paper discussing it. The scientists criticized Max's of proof, the theory, is the bad one, and it's bad. And the scientists criticized Max's proof of the theory is the good one. And so people have found, this is actually an example from the reading, which came from a different paper, have found that with an example like of proof as compared to proof of, you should see a positivity at 600 milliseconds. Again, as a person who cares about syntax, I don't know what that means. Because there's a lot of syntactic violations that aren't just, like another common example for this is I have many run to miles as opposed to I have many miles to run. They tend to just flip word order and call it a syntactic violation. And I don't know what that means. But that's a battle for another day. Anyway, N400s. This is what we're looking at. This is, I asked you in the quiz to talk about figures 1 and 3, so we're going to start at figure 1. And the limitations from question 3 on the quiz we already kind of discussed. Okay. So anyway, here's N400 in figure 1. Here we're seeing data from Han 2001. We have native speakers and Russian L2 speakers of German. Okay. Our example is something like, but in German, he spread the warm bread with butter versus socks. Okay. This is not the literal example, but this is the type of example. As you can see, semantically anomalous words like socks in our example are the dotted line. And the semantically normal words like butter are the solid line. Let's look at the natives because usually you have to look at natives directly. You'll notice L2ers will get L2 data and compare it, right? But the natives is really the most important thing. You can, if you look at the far right, they're trying to tell you what the numbers mean. So if you look at the far right where it says 0 and the x-axis is 0.5, 1, and 1.5, those are milliseconds, well, seconds actually. So 0.5 is 500 milliseconds, okay? So the first little tick mark under where it says native speaker, the first tick mark should be 500 milliseconds. And N400s were essentially onset 400 up to 600. Anywhere in there is counts as N400. So when a native speaker hears he spread the warm bread with butter versus socks, socks, the dotted line, is much bigger or more negative, because remember, negative is up for some unknown reason. I say this like I hate neurolinguistics. I really don't. I know I'm being very sarcastic, but I'm very unconvinced that we know a lot about what we're looking at. I think it's really interesting, but we don't yet know a lot about what it means. It's interpretive, and with that we should do research to figure it out, but it's interpretive, right? Even reading times are to some degree interpretive, okay? Anyway, so when a native speaker hears a violation versus the regular, here we're seeing an N400. It looks to me closer to 500 milliseconds, but you're seeing there's that distinction. And that's how they detect these quote components, is they do a control condition, a violation condition, and look for a change. Okay, so in the native speaker, we see much more negativity around 400, 500 milliseconds. The L2 speakers, it's much less pronounced. We are seeing a little bit more negativity for the dotted line, the socks, compared to the solid line, the butter. It's not very strong, but it's there. I think if you have something like this consistent across enough items and people, you would make an argument that it exists, right? You still have to run stats and such. So this is an N400, okay? Now P600, again, word order violations, aka syntactic, whatever that means. Again, let's take a look at the native speakers. Once again, the target is the solid line and the weird one is the dotted line. And the native speakers, notice that somewhere between 500 milliseconds and a second, so it looks kind of more like 800 milliseconds here, but that was in the range. Compared to the target item, the dotted line is experiencing more positivity because positivity is down in that time frame. So this is a P600, okay? We have more positivity compared to the control item. And we're seeing something also very robust in that sense for the L2 speakers. Theirs looks like it's a little bit earlier, frankly, which is more like a typical P600. You'll also notice that they sometimes, actually I won't get into that, that's fine. Anyway, so here you'll see that the L2ers are also doing it, even though it's slightly earlier in this particular experiment, okay? So that's the distinction between N400 and P600, that the idea is that an N400 is semantic, it's usually just a weird word swap, like one word. A P600 has been used for garden paths. It has been used for, and this is not really talked much about in our article that we read, it has been used for WH. You know, when you're doing studies where you're looking for the filler gap dependency and you're looking for, is this a gap? In reading times, you're looking for an increase in reading times. In neurolinguistics, you get a P600 where that gap ought to be. So I'm not proposing P600s are useless. I'm proposing that the idea of crazy word swaps being syntax is a bit odd. But P600 is used for lots of things that are actually, to me, better linguistics, right? Such as garden path garden paths, your brain goes, what? Or filler gap dependencies. And in some cases, you'll see both. And a lot of times you'll compare a native speaker to a non-native speaker and argue, did you find these or not? Or other applications are related to that. People have made studies of implicit versus explicit methods of teaching someone a second language. And to some degree, you find more native-like components, right? You find better P600s and N400s and all that. With people who were taught implicitly versus people who were taught explicitly. I think that's been primarily done with made-up languages, actually, as opposed to real languages, because they learn more in a short period of time, but you can use it for this. Okay, if you're interested in that particular study, I can refer you to the author, but send me any questions, and kudos in getting through